everybody. Welcome to the panel session. I have the pleasure to introduce you to Merck KGaA, Darmstadt, Germany. As seen here, we're the company behind the company, so we supply you with the materials that make everything we see in this show possible. Obviously, we're part of something bigger, so Merck KGaA Darmstadt, Germany is operating under various brands. We have a healthcare business named EMD Serono in the US. We have a life science business named Millipore Sigma in the US, and we have an electronics materials business named EMD Electronics in the US. And Merck is a very established company, 358 years of existence, coming from a town called Darmstadt in Germany, 63,000 employees, roughly 20 billion in sales, and 2.3 billion in R&D investments. So much to Merck, and now I'm handing it over to my co-host, Daniel.
Well, welcome to the panel again from myself. We're very excited to talk about photons. So the topic of this panel is called From Photons to the Future. And you'll see that in the next 30 minutes that everyone here on this panel is a big believer in the impact that photons will have on the semiconductor and the AI industry. And I guess reviewing from last year, I think we feel as believers in the photonic industry, somewhat validated that is becoming now actually the future, is becoming the present. And we see this with NVIDIA announcing kind of big moves towards co-packaged optics and their AI roadmap. We see this with large acquisitions that are happening in the venture capital industry, where we were fortunate enough to sell one of our portfolio companies called Celestial AI to Marvell earlier, a couple of months ago. And yeah, with that, we're very excited. We have very esteemed panelists here that have agreed to join us. And I want to invite each of them to introduce themselves. And we're going to start with Damien.
Thanks a lot, Daniel. So my name is Damien Tuleu. I'm French. You can hear with my accent. Okay. I'm based in Darmstadt, and I am the leader of the Optronics business at Merck KGaA, Darmstadt, Germany. And in Optronics, we are the ones who are really loving photons and lights. We have been dealing with lights for quite a long time now, because we are still the leading providers of display materials, such as LC, liquid crystals, OLED materials, and any other materials which will materialize light as part of display technologies. And why I like photons is because I do see that, with our capabilities that we have been developing for the last 50 years, now for us it's time to look for opportunities, how we can use those expertise and capabilities into the semi-environment where we see photons getting a larger role moving forward.
Yeah, hi, good afternoon. My name is Moren, and I'm the CEO of Polaris Electro-Optics. We are a US venture-backed startup in Colorado and Southern California, backed by our good friends of M Ventures. Our contribution is that we have developed a new class of liquid crystals that are enabling high-speed modulation, enhancing silicon photonics for all the future generations of datacom, and thereby continuing the path where silicon photonics has enabled the speed of data to go up and the cost of data to go down, which has really created this explosion in capacity that is the backbone of the AI data centers.
Good afternoon. My name is James Raring. I'm the CEO of a seed stage startup company named Lucidean. It's great to be here today. Thank you for having me. So Lucidean is a UC Santa Barbara spin-out. We just closed a strong seed round with a great syndicate, including M Ventures backing us. Our vision is to redefine data center optical links with our coherent class technology for the AI era. And we're doing this with a technology that we call Co-Zero. And Co-Zero brings coherent modulation with zero overhead. So we get all the benefits, the higher data rates, the higher link budgets, but with the same power consumption, same latency, and same cost as the incumbent direct detection technology used in data centers today. So we will be positioned to pick up right where the incumbent technology runs out of gas with our Co-Zero technology.
Okay, thank you so much. We want to keep this a high energy panel, so we're going to start off with a round of quick questions first and then go a little bit deeper afterwards. So the first question for each of the panelists would be around the idea that there is, obviously it's very, very hard to make semiconductors, to make the AI industry work, to make data centers work at scale. In your opinion, right now, in the electronics industry, what are the biggest pressing needs and opportunities for photons or photonics in general to address there?
So if I may start, and when you look at right now, how the semiconductor market is developing, definitely boosted by AI demand, which automatically will require more and more, data centers to sustain the demand. So what we see, in my view, what I see as maybe one of the main challenges is going to be about, either power consumption or data communication and bandwidth. And where we know right now is maybe photons could be a solution to try to deal and provide, I think, maybe a system and solution to reduce those needs in powers as well as to increase data communication and bandwidth.
Yeah, so what we've been seeing in the last few generations is every time we have doubled the speed, the reach of copper has become shorter and shorter. And we're now down to the level where maybe you can do 1.5 meters on copper before you need to start doing significant processing. So at that point in time, optics becomes a much better solution. Next generation, copper might not even reach within the rack itself. The following generation, maybe we need to put optics instead of PCBs so that the chips directly in the shelf communicate using optics. So I think this just follows a very, very long history of every time we double the rate, the reach of copper significantly reduces, and that's what you call the copper wall.
Yeah, fully agreed. It's all about the high-speed interconnects, right? With the explosion in demand for bandwidth density, data rates, signal integrity, copper just reaches its limits. So more and more, we're going to see optics extending down into shorter reaches, and this will be largely driven by the hyperscale and AI data center fabric.
Yeah, I think thanks a lot, and makes a lot of sense. If we take this one level further down, Damien, maybe starting with you, what do you see within the next 5 to 10 years the most, some concrete applications where light will have an impact in electronics?
Maybe we can definitely share also some opinion with Moren on that one, but I was referring before to our decades of expertise and capabilities in light through display technologies. And what we have been doing so far for the last 50 years is more or less basically bringing light into a semiconductor environment, because if you look at display panel, that exactly the same combination at the end. So for us, definitely, we see here an opportunity how we can now bring, I will say, the macro level of displays into the micro level of chips and CPUs, for example. Okay, and here what I do see an opportunity is really, I think, how we can build on our expertise in terms of chemistry, in terms of synthesis, in terms of computing simulation about molecules and how those molecules can be used now into application at the CPO level, for example. And I'm sure Moren will speak a bit more about modulator, for example, but that's exactly an area where we see ourselves, where LCs, which has been used for decades in display or even before that, can now find a new route of application to be maybe one of the solutions in terms of how we can basically convert electrons into photons and be now used for high bandwidth and high density basically communication, as well as less power consumption. But Moren, you can develop more than me on that one.
Yeah, I think it's a specific application. I think when you look at the AI factory with millions of GPUs, those will all be densely interconnected using optics. I think in the next 10 years, the speeds are going to be sufficient that even going within the card itself, you might have to use optics. And definitely as soon as you leave the card, it's going to be all optics. And the value in the AI data center, right, in the past, processor speed was important. But as we move into AI, interconnectivity of these processors is actually much more important than the individual speed. And to have this densely connected AI data center, you need also an equally densely interconnected optical backbone.
And so as a laser guy, I think I'll focus a little bit on the lasers here. The lasers are the source actually that generates the photons, which then replace the electrons in the high-speed interconnects. So it really all does start with the lasers for optical interconnects. And the data center is already highly dependent on lasers, right? All the pluggable transceivers that are pushing data from cluster to cluster across the data center, between data centers, between cities, between continents, driven by pluggable transceivers with lasers inside. The dependence on lasers right now is actually exploding. As the AI models increase in size, you need more compute power, you need more GPUs, going to millions of GPUs, and so you must connect the GPUs at data rates that don't bog down the whole system. So right now, the dependence on lasers is increasing, but over the next 5 to 10 years, we're going to see another stepwise change in this dependence. As we pull photons now into the electronics packaging for like co-packaged optics and optical input-output, now you're putting light into the package and pulling the signals out of the package in the optical domain rather than high-speed signaling. And what this does is it allows for a lot higher data rate or bandwidth per unit power and a lot more bandwidth per unit edge length. So this breaks down bottlenecks that currently exist in electrical SerDes and in electrical input-output, and will really enable this multi-hundred terabit system-level communication in and out of the packages.
Thank you. I think you guys are getting a good sense of high level, the opportunities and the challenges in the photonics industry. So let's dive maybe a little bit deeper with some individual questions. And the first question is for Damien. You have a very hard task. You run a business that is kind of almost the job to marry two industries, as you just said, right? The semiconductor industry and the optical, photonical, and maybe liquid crystal industry, right? Where do you see the biggest challenges there, right? Is it in the materials? Is it in the processes? Is it in the actual physical packaging of those two worlds? Give us some insights there.
I believe there are challenges across all the different, segments that you were referring before. On materials, I see more opportunities than challenges. Because, as I said before, we have definitely, the backbone of being the company who can really, work on our library of 20,000 singles, LCs, and find ways, I think, how those one can respond, to maybe a specific requirement for modulation, for example. But as you were saying before, also, material will play also, new material will play also key roles in waveguide, for example, which will be required also to, enhance the way how we have to transport, specific, communication. So materials, for me, I do see that as a challenge, but also as an opportunity. The other area where I do see also some challenges is concerning the packaging, okay? Because we know that those ones will become more and more complex, okay? And we, MEC, KGA Darmstadt, Germany, we have now investing into metrology inspection, which gives us also now the opportunities to find out how we can also enhance our platforms to really now respond to those even more advanced packaging where I expect that more minutious dimension metrological application will be required, which automatically will create also some no needs in terms of metrology inspection. And the last one maybe could be around, processes and systems, because right now, if you look at, the industry, it's a bit far behind to what has been developed in the semi area. I understand right now there is not so much standardization, so definitely the industry have to mature to become with some standards, which automatically will create a bit more opportunities in terms of system and processes. But Moren, you can develop it more on that one.
Thanks, Damien. James, as the laser guy, you could argue lasers are already ubiquitous in the data center, right? And or in every pluggable transceiver, you have a laser, obviously. What's, in your eyes, sort of the emerging challenges for lasers that new products would have to tackle, and what are you focusing on in terms of R&D on the laser side?
Yeah, great question. So absolutely, lasers are already ubiquitous through data centers, but as we've been talking about, we're moving to do co-packaged optics to bring the light into the electronics package, right? And so that means that the lasers themselves or the light output from the laser will need to be in vicinity of the high power silicon. And this is a very hot and extreme environment. So it's critical that there's design for reliability, design for manufacturing, that when you're looking at how you're laying out your architecture, that you can maintain efficiency over temperature and maintain reliability at very high temperatures. And people that understand the semiconductors understand that reliability and efficiency usually go down with temperature. So it's kind of fighting physics, and that's where smart design comes into play. As you're relying more on the optics inside these the packages with the computer processing going on, failures make a bigger difference, right? One failure, one drop in efficiency can touch millions of devices, so the stakes get high. At Lucidean, we're designing for a lot of integration for low coupling losses, high efficiency, and high manufacturability. And one of the kind of benefits of our coherent technology is that we can use lasers that are very standardized, they're tried and proven, what's called a distributed feedback laser, and it doesn't require temperature stabilization or cooling. And I think that's a very big point as these lasers get into the electronics. They can't be looked at as like discrete components. They have to be viewed more as like platform, a scalable platform, and become part of the ecosystem, the electronic ecosystem.
Super, thank you. Moren, so you're kind of in between, right? Physically and also what you work on. So you have a materials component, but obviously you're also working very closely with the laser folks. Give us some insights, right? A modulator is a very, very tiny piece, but it can have a very big impact on a system level performance. How does that play out?
Yeah, so the modulator itself is the key item actually when you build a pluggable transceiver. The laser is really a lamp that helps us provide the source to modulate all the precious information on, and especially using external modulation techniques, which is what our company does, right? We build the Maxenter interferometers using our own liquid crystal material to push the speeds well beyond what you can do with silicon photonics alone. And in that case, all we need is CW laser source, either local or maybe as recent CPO approaches are doing, where they have high power sources that get split out. When you look at the challenge of getting up to these very, very high speeds, basic technology right now is stalled out at about 200 gig per lane. silicon photonics. Indium phosphide pushes beyond, but it's becoming progressively harder. So that's really where these new materials, and in particular our material plays, is that we can enable 400 gig per lane in the data center, and we can also push to 1.6T and beyond in the coherent space. The final comment I was going to make is another challenge for modulators is to become sufficiently small that we can actually put them into CPO. Because one of the challenges that people are addressing right now is, should we go fast and wide, or should we go slow and wide, or should we go fast and narrow, or perhaps in the future we really want to go fast and wide. So to do that, we need really fast modulators, but we also need them to be really compact. And that's another technology challenge for many of the common modulation schemes like indium phosphide, thin film lithium niobate, is they don't lend themselves really well to become very compact modulators. And again, that's another place where an organic material like the ferroelectric liquid crystal allows you to make much, much smaller modulators.
Got it, okay. So I want to turn it back to James, one, so he can defend himself against the statement that lasers are just lamps. But second, James, if you could comment on, I think one of the trends that we're seeing is that obviously a lot of the market demand is driven by the hyperscalers, and hyperscalers have their own roadmaps, and I think there's been questions around whether, especially for someone that supplies into these hyperscalers, whether that ecosystem seems to be converging to one solution or diverging into multiple approaches. And then for you as a supplier into that ecosystem, what does that mean for actually building products, thinking about interoperability between those products while going after these very large opportunities right now?
Yeah, another great question. So I think we see kind of like a hybrid trend with the hyperscalers. So on one hand, each of the hyperscalers are optimizing their systems, their architectures, how they're putting together the GPUs when their networks for their specific workloads, right? There's different models that they're trying to optimize on how fast can they solve the models. So there is a divergence at the system architecture level. But when it comes to the components, the building blocks, right, we're seeing a convergence, right? So standards, having universal interfaces, having like light engines that are standardized is very important, because having these common interfaces can bring scale, it can bring the cost structure and the reliability to the levels that are really going to be demanded by the industry. So on one hand, you see this divergence of how the different building blocks are being put together, but on the other, it's a convergence with making sure that the components and the interfaces are standardized. And that brings me to like interoperability, right? Designing transceivers or links that can work with different protocols, or having multiple supplier agreements, MSAs, right? This reduces the integration friction. When you're bringing a new technology to a hyperscaler, if it's something kind of wild and out of left field, there'll be a resistance to adopt because it's unproven. So if you can develop standards and the capability to operate with different architectures, this reduces the anxiety and the friction. Another big thing here is design tools, right? So being able to simulate your optics and model the optics very precisely before you bring them to a product. This is key because you want to get it right on the first pass. So when you're manufacturing these chips, it can take 6 months, it could take more than that for a tape out. So if you have your designs wrong, that will set you back 3 quarters, and you can miss an entire commercial window. So tools like simulation and modeling are really critical also for smooth transition and smooth integration.
Thanks, James. Morten, you mentioned copper running out of steam at the very beginning, and I think that's sort of a theme that the entire industry has bought into, and everybody's constantly bringing it up. At the same time, copper is still used for a scale-up network everywhere, and all the copper guys are always saying, yeah, optics is great, but it's too expensive, right? Where do you see those sort of beachhead markets where optics will hit first on the shorter reach side, where the benefit is so large that it outweighs sort of maybe the cost disadvantage?
So if we look at scale-up networks, and you look within the racks, the copper cables that are needed to actually enable that interconnectivity are very, very bulky. And so you already today have multiple architectures where companies have switched to optics, even for scale-up inside the rack instead of copper, simply because the copper cables are thick. They can barely reach from the top to the bottom. And that's also one of the reasons why you see NVIDIA is heavily investing into CPO. But at the 200 gig per lane generation, copper is still feasible. Go to 400 gig per lane, reach of copper probably goes down about a factor of 4. And suddenly the 1.5 meters you can do without excessive processing gets into tens of centimeters, and at that point in time, copper has effectively run out of steam, at least for scale up within the rack.
Yeah, makes sense.
So I think at the end of the day, whenever you can do simple copper, you want to do simple copper because it's the cheapest solution. But the moment you have to run through hoops, including DSPs on the copper itself, suddenly the whole idea of doing copper starts becoming very unattractive.
Makes sense. Thanks. Damien, as we're coming up to the end, sort of a nice finishing question for you. If you fast forward 10 years, what's sort of the one consumer application or service that you would like to see leverage photonics and nobody knows about it? Like the DVD player was 10 years ago or something. What do you think in 10 years in the future, what's that consumer application or service that leverages photonics?
I think it's a good question because we are here sitting at CES, meaning consumer, electric show. And if I look at our booth here, I may see maybe two applications. And both of them are related to the same objective, which is to provide, to the consumer healthcare information. So one could be definitely using healthcare, digital healthcare that you see on the booth, but basically on your smartwatch. Okay, where, for example, by using photonics structures, you will be able to more or less be able to sensing, the different kind of body, fluids, where you can monitor, your glucose, you can monitor your lactate, you can monitor your heart pressures, and that being done thanks to, photonics platforms. And the other, I believe, consumer device could be also AR glasses, where right now we are looking at them for, creating a kind of virtual environment, but you can imagine in the futures, thanks to, a photonics platform and enhancement, you can now also having sensors who can monitor, your fluids like through the tears and look at, any specific maybe disease that you may not know that you have, and to be able, to prevent yourself. So that for me, I think what I do see moving forward, where applying photonics on chip level, where we can definitely manage data, and for example, being able, to also sensing through different wave lengths, for example, where you are moving, for example, spectroscopy from a big platform to a small wearable device, could be also thanks to photonics application. So that's what I can see within the next 10 years, but we have time to see that happen.
Awesome, thank you. I think that's it. Time is up. Thanks for the attendance and the audience, and thanks for the panelists.
Thank you.